Hello and welcome to this video. In this video we shall be talking about the Gauss law. This is the fourth video in the module of electrostatics for class 12. Before talking about the Gauss law, we first talk about the idea of the electric flux. In a physical scenario, the electric flux give us an idea of exactly how many lines are crossing a certain surface. If we think of, for example, a velocity field, for example, in that case the flux can be associated with the amount of liquid or the fluid flowing per unit of time, in fact. But let us first define what is the flux of the electric field or the electric flux before moving over to the application or the Gauss law actually. Now the simplest possible situation that we might have is that we have a uniform electric field E in space and there is a plane surface whose area is equal to capital A, and this is immersed in the field and oriented perpendicular to the electric field. That is situation shown something like this. We have in this case electric field. The field lines are basically these arrows which are in this case piercing this area capital A, and this area is oriented perpendicular to the electric field. In this case the flux of the electric field can be simply defined as the magnitude of the electric field, that is mod of E multiplied by the area. This is simplest possible scenario. So basically the flux is nothing but the electric field multiplied by the area. Now what might happen is definitely the situation might not be as simple as this. We might have, for example, the electric field and the area oriented not exactly at right angles but at some other angle. So for example, we may consider the area in the previous situation is being turned by an angle theta, and we have a situation like this. In this case, this particular angle over here, this is the angle with respect to which or by which the plane area has been turned with respect to its original orientation that we saw in the first case. So in this situation, the idea is to consider the projection of the area A back onto the original plane. So if I consider this area A over here and we just try to project it back over this particular original orientation, which is very lightly visible over here. In this case we can define the flux in terms of the electric field, the area and this angle theta. In fact, the projection, if I have an area, the area they project very much like vectors actually. If I have for example a rectangular area and I want to project it on a different plane, not obviously in this plane of this rectangle the area is just, say for example, A. Now if I just want to project in a different plane, in that case the area of the projection, the shadow, will be nothing but A into cos of the angle between them. Fine. That is how the area project. As I said, it's very similar to the vectors in fact. So in this case what I could do is we could project the area back on the original orientation, or there's a different way that we could do this. First of all, in this case we can simply multiply the electric field and I said the projection of the area back onto the original orientation that we had in the first case, which is therefore A cos theta, because I said the vectors, the area they project as vectors, and therefore in this case the projection is going to be nothing but A cos theta, and therefore the flux now can be defined as the magnitude of the electric field into A into cos of the angle between the plane now and what was the initial orientation, which was perpendicular to the electric field. Now, better way to write this particular result down by using the dot product of vectors. Now, in order to do so, what I need to do is first define the area vector. Now, the area vector is, we are going to think of area as a vector quantity. The magnitude of this vector is nothing but the area of the plate itself, or the plane that we are considering, while direction can be taken to be along the normal to the surface. So, for example, if I consider an area like this over here, now the area vector needs to be, or it can be taken to be a vector pointing in the normal direction, which is perpendicular to the plane. So, this could be taken as the area vector. The magnitude will be nothing but the area of the surface that we have over here, while the direction is going to be the direction perpendicular to the surface actually. Now, obviously in this case we could have two directions actually, one pointing upward that we have seen, or the other one which can point in the downward directions. So, as far as the area vector is concerned, I could take any of them over there. There is no any such rules. However, as we shall see later on, if we have a closed surface and in a particular application, it will be useful to take the area vector to be the outward normal. But right now in this case, we can take the area vector to be any one of the directions. Fine. So, with this particular idea in mind, we could look at the previous result. We see that the electric field, I have removed most of the other vectors, or rather the arrows, lines actually. And the area vector in this case is pointing perpendicular to this plane over here, and the angle between, you see that this angle which was originally we took, the angle between the two planes, is still the angle between the area vector and the electric field. As a result of which, in this case, we could utilize the dot product of two vectors and write down the flux as simply E dot A, because it was E into the area into cos of the angle between them. So, it can be written down as simply E dot A. So, this is the fundamental definition of the flux. Is basically a dot product of the electric field and the area. As such, the SI unit for the flux can be written down as the SI unit of the electric field, which is Newton per Coulomb, multiplied by the area, which is square. So, I get Newton meter square per Coulomb, or later on we can see that it will be also written down as voltmeter in fact. But right now for the moment it is Newton per Coulomb into meter square, or Newton meter square per Coulomb. Fine. Okay, now obviously in a very general scenario, we might have an electric field which is non-uniform and the area which is no longer a plane surface. We might have a curved surface. So, we have a general situation where the electric field is not uniform and the surface is curved, no longer a plane surface but a curved surface. So, what to do in this case? We can have an example situation something like this, where we have a curved surface. You see these field lines that we can see, they are divergent in a sense. So, that's represent a non-uniform electric field. Then we have over here, I have shown in this case different regions where the electric field lines and the area vector, they are actually oriented in different directions. So, all these are possibilities. The idea that we do over here in order to define the flux to the entire surface, as it has been done in this diagram, we divide the entire surface into a large number of small areas. Now, exactly how small, that depends on two things. First of all, the area vector should be, or rather the pieces, the parts of the surface, they should be small enough so that the variation of the electric fields in that region could be neglected, even if there are. I mean, if the electric field changes from one point to the other point, I am going to take the parts or the areas to be so small of each of the portions that any variation of the electric field could be neglected. And secondly, the parts must be small enough so that the curvature could be neglected as well. So we can treat the surface as if it was just a plane surface. Fine. With that thing in mind, you can see that in this diagram, for example, we have a few pieces shown where the area vector and the electric field vector are oriented in a different way. For example, in this case, the angle between the electric field and the area vector is more than 90 degrees. In this case, it's exactly 90 degrees, while in this case, the angle is less than 90 degrees. So all the situations can arise because in this case, the electric field is non-uniform and the surface is a curved surface. So any one of the situations can occur. Now to define the flux in this case, what we do is to divide the surface into large number of small areas, which we already done, and I'm going to consider one such area as dA vector. So this is a differential element. For example, you might consider over here this portion over here and call the area over this point as dA vector. dA vector is basically going to be different for different pieces because the surface keeps on changing, so normal keeps on changing as well. Now, if the electric field at the location of the differential element that we have taken up, dA vector, is capital E vector, which again can be different. It can change from one location to the other location. But at the site of dA vector, I am taking this to be E. Then I find out the contribution to the total flux by this little portion as d phi, which is E dot dA. That gives us a scalar number. So if I do this over every part in this case, every portion over here, I am going to get large number of scalar numbers. For every small section of the entire surface, I am going to get a certain scalar number which might be positive if the angle between E and dA vector is less than 90 degree, or it might be 0 if the angle becomes 90 degrees over there, or it might be negative, which will happen, for example, if the electric field vector and the area vector are having an angle which is more than 90 degrees in fact. Fine. So what I do is I compute in this case E dot dA for each of those little parts, and then I need to add them up. Now obviously in this case the summation is not exactly a discrete sum, but rather a continuous sum over there. So instead of sum, we need to use a integral. Fine. And therefore what we end up getting is a general definition, the most general situation of the flux of the electric field as the integral of E dot dA vector over a surface, the surface on which we are trying to compute the flux. Though we have written down this case a single integral sign over here, keep in mind this is a surface integral which is implied by this differential element dA vector. So dA vector is actually a small area vector, and therefore the flux is basically the evaluation or integration of the electric field over a surface. Fine. Now, as I said already, for an open surface, there are two possible directions of the area vector. I could take up one direction or the other way up. For example, if I have a surface like this, I could take the area vector to be pointing this direction, or I can take it to be pointing in the opposite direction. And they both are going to be possible orientation for the area vector. However, when we are finding the flux through a closed surface, a closed surface is something which is dividing the entire space into two parts, one is inside, one is outside. Fine. So in a situation where we have to find out the electric flux through a closed surface, the convention is to consider the outward normal as the direction of the area vector, the outward normal. Fine. So at every point we know what is inside and outside, so I must take out in this case the area vector which is pointing in the outward direction. Okay. At the same time, because a closed surface, the integration over a closed surface is indicated by putting up this little circle on the integration. So what will happen is, if I put this circle on the sign of integral, it means I am talking about an integral over a closed surface. Fine. So that will be therefore the flux through a closed surface, which we shall see is useful for the Gauss law. Now we should notice that while computing this flux of the electric field, the surface that we are dealing with, this need not be a physical surface, okay? It might not be a real physical surface, rather it has to be a hypothetical surface. So it's surface that we have constructed imaginary surface. It's not exactly something which is physically present over there. Fine? Okay. Now with this particular idea of the flux, by knowing that flux is nothing but the surface integral of the electric field, we can now look at the Gauss law. It turns out Gauss law is a law which actually gives a quantitative relation between the electric flux through a closed surface and the net charge which is enclosed by that closed surface. It turns out that Gauss theorem, or the flux rather, you could think of the flux as if it is a measure of how strong. By knowing the flux through a surface, I can tell how strong the source is, implying whether there is a large amount of positive charge or less amount of positive charge. For a analogy, for example, consider that there is a sink, fine, and you have opened a tap above it, and there is no outlet, so only the water is being filled. Now once the sink overflows, by measuring what or how much volume of water is coming out or flowing out of the sink, we can actually get an idea of the strength of the tap above it. So if the tap is allowing water to fall at a very fast rate, then more water will also fall through the overflowing sink per unit of time. So if I just measure how much volume of water is flowing in 1 second, overflowing in 1 second, then I can actually get an indication of how much water is actually being put inside that sink. Okay, this is the idea of the Gauss's law actually. By measuring the flux on a surface, closed surface, I can find out how much is the net charge present within that surface. Okay, so the Gauss law basically gives us a quantitative relationship, so in terms of an equation actually, between the electric flux through a closed surface and the net charge that is enclosed by that closed surface. So the statement of the Gauss law that says that if you look at the flux of the electric field through a closed surface, it is equal to 1 by epsilon times the net charge enclosed by that surface. Or if we write down in a mathematical way, because the flux is computed as E dot dA for a closed surface, therefore if I look at E dot dA for a closed surface, that is a flux, it's going to be equal to Q enclosed by epsilon naught. Okay, Q enclosed is basically the algebraic sum of all the charges that are present inside the surface. So if I have, for example, this surface over there are charges, for example, Q, then we have got minus 2Q, and then we get, say, for example, plus 5Q present. Then in this case, if I look at the Q enclosed, the net charge actually, the Q enclosed is in fact nothing but the algebraic sum, which implies over here that it is the sum together with the sign. So I'll have this one Q minus 2Q and 5Q, the sum of it, and that will give us basically 4Q. So this becomes in this case the enclosed charge. Okay, so basically the enclosed charge is nothing but the sum total of all the charges together with the sign which is inside the surface. Fine. You should notice a few things regarding this Gauss law, which is a very important point. First of all, the Gauss law is true for any closed surface, no matter what shape and size. It can be applied for every closed surface, whether big or small, doesn't matter what size is. But remember, this is nothing but a hypothetical surface actually in any case. Fine. Now if you look at the Gauss theorem, the Gauss law, the left side contains E dot dA, Now, and the right side is Q enclosed by the epsilon naught. The point is over here that if you look at this electric field which appears on the left hand side, this one over there, this electric field is not actually due to only Q enclosed, but rather due to all the charges, whether inside or outside. So all the charges, they contribute to the electric field which appears over here. However, the right side contains only the enclosed charges. Fine. The right side doesn't contain whatever is outside. If something is outside, it doesn't appear over in that right side actually. Fine. The surface over which we are going to compute the flux for the purpose of this Gauss law, we shall call it as a Gaussian surface. This is just a name, just to so that we know that what we're talking about over there. We shall talk about the Gaussian surface, and that will be the surface over which we try to compute the flux for application of the Gauss law actually. And I was saying, if there is a charge which is present inside a surface, for example, this Q. Now with this charge inside over here and this surface, there is some flux. Flux or electric field is nothing but, in this case, Q by epsilon naught, because only one charge present. Now if I move this charge from here to here, for example, now this comes over here, it has not gone outside, it's yet inside, but moved from one position to the other point. So now the point is that, you see, with this movement of the charge from one location to the other location, the electric field has changed everywhere. Everywhere implies at every point of space, including those points which lie on this Gaussian surface, or this surface basically. So electric field has changed at every point on this particular surface. It has changed over here, it has changed over here or here. However, interestingly, the flux has not changed. If I look at the surface integral E dot dA, that has not changed actually. Though the electric field will have changed, but the flux will not change as long as the charge is not going outside. Fine. As long as we are at the charge is inside the surface, the flux remains unchanged. That's very interesting about this flux, or the Gauss law rather. And we also notice that the Gauss law is always true. So it's always true implies in all cases that we can think of, the Gauss law will be true, electrostatic field. However, it is not always useful. Okay, when I say useful, I intend Gauss law to, to find out the electric field, to use the Gauss law in order to find out the electric field due to some charge configuration. So if I wish the Gauss law to be useful for calculation of electrostatic field due to a certain system of charges, then there has to be some kind of symmetry involved, right? The charge distribution must be symmetrical. Symmetrical in the sense that, by either, turning it about a point or about a line, we should not be able to distinguish between them. Okay. So this symmetry is important, otherwise we won't be able to apply this Gauss law to find the electrostatic field. We can obviously apply the Gauss law in order to find out the flux, or for example charge enclosed, that can be done. But finding the electric field will require us to have certain degree of symmetry for the charge distribution. Okay. As we shall see, there are usually only three symmetries involved. One of them is the spherical symmetry, where the properties are dependent only on a distance from a fixed point. The other is the cylindrical symmetry, where the properties depend only on the line, distance from a fixed line actually. And we shall look at the planar symmetry as well, where the properties will be dependent only on a distance from a fixed surface actually, fixed plane rather. Fine. So those are the only three symmetry that we should be dealing with. We also should notice that this Gauss law will not be valid, for example, if the Coulomb's law were not an inverse square law actually. So if the Coulomb's law in the denominator it was not r square but some other power of r, then the Gauss law will no longer be valid. This actually helps in proving the Coulomb's law indirectly, by the way. In fact, we can by using the by finding out certain properties, by applying the Gauss law, if you kind of verify those properties and they turn out to be correct, then it will imply the Gauss law is correct, and that also will imply that the Coulomb's law is valid actually. and it turns out had the Coulomb's law dependent not on 1 by r square law but some other law, then Gauss law will not have been applicable. Fine. So that is what we have regarding the Gauss law and the idea of the flux over there. Thank you for your attention. We shall be meeting in the next video, which will have some applications regarding the Gauss law.